Okay, we are back for excitation, contraction, coupling. So again, there was a really great animated YouTube video. If you haven't watched that 2-minute video, please watch that prior to going through this lecture. And so you can find that here. I've embedded it on our modules. So the strength of a muscle contraction equals the number of motor units recruited. We've also discussed how as you age, the number of motor units recruited declines, and that can lead to sarcopenia, less strength. And so we know that a motor unit is a motor neuron and all the muscle fibers that it innervates. So I really like this kind of simplified version of the sequence of events in skeletal muscle contraction. So the past few lectures and videos that you've watched, we know that we have this neural control. So when a skeletal muscle fiber contracts, when stimulated by a motor neuron at a neuromuscular junction. So this stimulus arrives in the form of an action potential at the synaptic terminal. So we have this action potential that arrives, and this causes the release of acetylcholine into the synaptic cleft. So that's sort of what we are depicting in this animation right here. We have this excitement, which is why this is called the excitation contraction coupling. So the acetylcholine diffuses to the motor end plate, binds to the receptors, and leads to an action potential. So this action potential in the sarcolemma travels along the T tubules, where it triggers the release of calcium ions from the terminal cisterine of the sarcoplasmic reticulum. So this contraction cycle now begins, and it will continue as long as ATP is available. I know we haven't spoken a lot about ATP. It's coming. So just kind of tuck that back in your brain. We are going to talk a lot about ATP, but this is the energy. This is the currency. This is what we're using to actually carry out muscle contraction. So it's available, and action potentials are still being produced at the motor end plate as long as calcium is available. So then the thick and thin filaments interact, the sarcomeres shorten, pulling the ends of the muscle fibers closer together, kind of like the rungs of the ladder. Again, I think the YouTube video prior to this did a really good job kind of visualizing what is going on with the actin and the myosin in terms of this contraction and this coupling and causing this skeletal muscle contraction. So during contraction, the entire skeletal muscle shortens, so it produces this tension, it shortens, and it produces a pull at either end. So again, this is just sort of a kind of a quick overview. Hopefully this isn't anything too new that you remember from Human Systems Phys or a previous class, but this was the sequence of events in the skeletal muscle contraction. So this sliding filament theory, also known as muscle contraction, is this actin and myosin sort of working together, pushing and pulling, so that we produce this shortening and this muscle contraction. Again, I think the YouTube video prior to this shows a really good visual of what is going on during the sliding filament theory. So make sure that you're comfortable and you understand sort of the mechanisms and sort of the molecular underpinnings at play that feed into muscle contraction. So we know troponin and tropomyosin are two regulatory proteins that control muscular contraction. We know about 12, but really these two are the most important. So when this action potential reaches the sarcoplasmic reticulum, remember that's where the calcium is stored and then released. The calcium diffuses into the muscle and binds to troponin. So this is the trigger step in muscular contraction. When that calcium is released and binds to troponin, this is the trigger step in muscular contraction. And so the trigger for contraction is linked to the release of stored calcium in the region of the sarcoplasmic reticulum. So when a muscle is relaxed, the concentration of calcium in the sarcoplasmic reticulum is low. However, when this nerve impulse arrives at the junction, that's going to trigger the release of calcium. So this calcium will bind to troponin, which allows these active sites on the myosin to be uncovered. And then this energizes this myosin cross bridge, so the actin molecule can result in this muscle shortening. So this is why troponin and tropomyosin are very integral to this process, and why this calcium releasing, diffusing into the muscle, binding to troponin is known as the trigger step for muscular contraction. Now, this is a really important concept to understand. How long can this muscle contraction go on? So we know that ATP attaches to the myosin cross bridges and provides the energy necessary for binding. And so this can be repeated as long as there is enough free calcium available to bind to provide the energy. So failure of a muscle to maintain enough calcium or hydrolyze this ATP causes muscle fatigue. So we've all been there, right? We've all been at the end of a 5K. We've been at the end of our reps for bicep curls when we're like, oh my goodness, I just don't have enough energy to keep up this contraction. And that's due directly to not having enough calcium stores and maintaining that calcium to hydrolyze the ATP, which is going to cause the muscle fatigue. So we need calcium to help with our energy production and our ATP to lead to muscle contraction. If we don't have that calcium, we will not have our muscle contraction. So another way, I like to give kind of several visuals. Again, I'm such a visual learner and some things work better for me. So hopefully with these different kind of examples I give you, it will help to sort of understand. So first, for the sliding filament theory, again, this is nothing new, just again, kind of reiterating some of these same points. You first need energy. So the myosin head, it's a high energy configuration. And then we have the binding and the attachment. So the myosin cross bridge attaches to the actin myofilament. This works the stroke myosin heads, and it bends and it pulls the actin filament, sliding it toward the M line. So then we have the flex and the power stroke. And so this allows ATP to attach to the myosin head. The cross bridge detaches. So we have this detach and release. And then ATP is split into ADP and pi. Cocking of the head of the myosin occurs. And then if there is enough calcium available, we can repeat this process again. So again, in just another way, we know the sliding filament theory, we need our energy, we need the binding and attachment, the power stroke, and then the detach and the release. So whichever visual I've provided here that really kind of helps you to understand this along with the animations of the PowerPoint video, I'm really hoping that you kind of have a good grasp now on excitation contraction coupling and what's going on molecularly for skeletal muscle contraction. So as we sort of wrap this up and go in for our next lecture for the energy for contraction, it's important to know that we have three sources for ATP production. So this kind of currency, this energy for our bodies to produce muscle contraction, to produce work. We have phosphocreatine, we have glycolysis, and we have oxidative phosphorylation. And so these are our sort of three energy sources for ATP. I'm going to go a lot more into sort of this schematic and this visual in the coming lecture, but I just wanted to introduce some of these concepts so you kind of know what is coming up. So just to review for the excitation contraction coupling, we know what regulates the interaction of actin and myosin and therefore muscle contraction. So step one, we have a nerve impulse arriving at the neuromuscular junction. This releases acetylcholine. This acetylcholine binds to receptors on the motor end plate, producing an end plate potential. And then we have a depolarization of the muscle cell conducted down the transverse tubule. And when the action potential reaches the sarcoplasmic reticulum, we have calcium that's released. And this is sort of the trigger step in controlling muscular contraction. Are we going to still have those calcium stores there? Do we have a lot of them? Are they becoming depleted? That's why it's called the trigger step. So we also have troponin and tropomyosin, which will help to regulate this contraction by controlling the interaction of the actin and the myosin. So if you want to pause the video and sort of do a check your understanding, I have provided this opportunity for you to put in the correct order, starting with the nerve impulse travels to the neuromuscular junction and ending with the impulse stopping. Go ahead and see if you can put these in the correct order to help kind of check your knowledge for the summary and understanding of muscular contraction. So stop the video now and work on that. Okay, so what we learned in this module, the process of muscular contraction can be best explained by the sliding filament theory. This proposes that the muscle shortening occurs to the movement of the actin moving over the myosin. And I've already sort of talked about these step by step for muscular contraction. So I really hope that you have a good understanding of this. And we're really going to dive more into this and apply this to exercise physiology in the coming modules. See ya on the next one.